This is the first problem I'll try. We have a circuit here operating at 2 kilohertz. Phasor magnitude is 0 to peak. I think it always is in these problems. And the question is, how much reactive power is supplied by the voltage source? So, I have copied out this circuit earlier. Let's just flip over to it on a piece of paper so I can scribble. I want to know the reactive power. Well, reminder that the reactive power is the imaginary part of the complex power. Now, an imaginary part of power is associated with capacitors, not resistors. Resistors are going to give you an active power. If I've got a voltage here of 310 microvolts, which I do, then I'm going to get a current flowing down through this resistor here of 310 microvolts divided by 12. And it's going to be in phase with the voltage. That is going to give me a real power, an active power. That's not what I want. The question said reactive power. The reactive power is going to come from the imaginary part of the complex power. To get an imaginary part, if we remember the formulas here, S equals V times I complex conjugate divided by 2, and in particular the form of that says S equals the magnitude of V squared over 2Z complex conjugate. Well, this is going to be complex. What I want is the imaginary part of it, because that's the reactive power. The real part of this would give me the active power. If I want just the reactive part of this, the imaginary part of this, then Z has got to be an imaginary number. I need an imaginary impedance. The capacitor is going to give me an imaginary impedance. The resistor is not. So, I could work out the complex power in the resistor. That would just be V squared divided by 2 times 12, but that's real. I could work out the imaginary part in the capacitor, and that would be the magnitude of V squared, so 310 microvolts squared, divided by 2 times the complex impedance of the capacitor, which is 1 over J omega C. And that is going to be imaginary. So that's the power that I want. How big is that in terms of its imaginary component? Well, that's going to be, let's see, multiply top and bottom by J. I will get J times 310 times 10 to the minus 6, because it's micro squared, divided by 2 over omega C. Well, the frequency that I'm operating at here, if I go back and have a look at the question, was 2 kilohertz. So, my omega is going to be 2 pi times 2 kilohertz, 2 times 10 to the 3, and the capacitance is 22 micro, or 22 times 10 to the minus 6. That gives me, come over here, give me some more room, J times 310 times 10 to the minus 6 squared, over 2, bring this lot up here, times 2 times pi times 2 times 10 to the power of 3 times 22 times 10 to the power of minus 6. And if I get out a calculator and chuck all of that into it, then the answer that I get should be 13.28 times 10 to the minus 9. And I would use the units VAR here, VAR, because it's a reactive power. But all I'd have to enter into the quiz app to get the answer is 13.28 times 10 to the minus 9, or you could just write that as 13.28 N for nano, and the quiz app will know what you mean. Right, that's the first one. Let's try another one. this is the second one that we'll try. Here we've got a current, this time is defined, of 100 microamps, and that's flowing through a 220 ohm resistor and a 15 millihenry inductor. The frequency of the circuit is 20 kilohertz, and the question is asking for the apparent power. Okay, well, the apparent power is the magnitude of the complex power. So all we're interested in is the magnitude of S. Go and have a look here, and what we were interested in is the magnitude of S. Okay, S, as we know, is the 0 to peak phasor voltage times the complex conjugate of the 0 to peak current voltage divided by 2. Now, we know the current here, we don't know the voltage, but we do know that the voltage phasor is the current phasor multiplied by the complex impedance in the circuit, and we know that therefore the current phasor is V over Z, and take the complex conjugate of this lot, we would get that. We can substitute in for, actually wrong way round, I want to get rid of V, don't I? Not I. Substitute in for V and get S equals I times Z times I complex conjugate divided by 2, which is the magnitude of I squared times Z over 2. Right, we know the current. What's the complex impedance in the circuit? Well, complex impedance of an inductor is J omega L. So the complex impedance in my circuit, since these two components are in series, is 220 plus J times omega, which is 2 pi times 20 kilohertz, times L, which is 15 millihenries. So quite conveniently, that kilo and that milli cancel out. That would give me here 220 plus J times 2 times pi times 20 times 15, 2 times pi times 20 times 15, which is 1885 approximately. Right, that's Z. So S equals the magnitude of I squared, which is the magnitude of 100 micro, which is 100 times 10 to the minus 6 squared, divided by 2 times Z, which is 220 plus J1885. And if I work out what this is in terms of a real and imaginary component, it would give me 1.1 times 10 to the minus 6 plus J times 9.425 times 10 to the minus 6. And I want the magnitude of that. Apparent power is the magnitude of the complex power. The magnitude of this, I've got the real and the imaginary parts. I can get the magnitude by good old Pythagoras. Magnitude of S would just be the square root of 1.1 times 10 to the minus 6 squared plus 9.425 times 10 to the minus 6 squared, which, if I plug in the numbers correctly, is 9.49 times 10 to the power of minus 6. And I'll express that in units of VA, volts amps, which is the typical unit we use for apparent power. Oops. And that's that one done. Okay.